Now, since damping is such a big problem, how do we fix it? Remember when you're on a swing and the swing starts to decrease its amplitude? What do? You either lean back and try it yourself, or you have somebody push you, like a mom or dad or somebody when you were little, they would push you on the swing set. That is now called a forced oscillation in physics. So you're forcing the oscillation to maintain its amplitude. So if you don't want to go any higher, you can have people push you at just the right amount. And that in physics is called a forced oscillation. So just a fancy word of saying, I'm going to push you properly. And in general, that forced oscillation is done by the means of a crankshaft. These are also called driven oscillations, especially when they are being driven by a mechanical means, like by attaching a battery to the system or attaching a generator to the system, or somehow externally providing the force that will keep it in motion. Do you remember this picture when it just went damped and now it's not? Because every time it starts becoming smaller and smaller, a machine makes it so that it doesn't lose its vibration, its amplitude. And that's like your mom and dad pushing you on a swing. Just the right amount, just the right amount that you want. And what is just the right amount? It's called resonant frequency. This is the resonant frequency. It is also called the natural frequency of the system. It's also called the natural frequency of any system. So everything resonates by a particular frequency, and every single thing that we build has a different resonant frequency. How many of you were in a marching band in high school? 2, 3, okay. Good. Have you ever gone over a bridge marching? What do they tell you to do when you go over a bridge? Or what should they tell you to do? So the marching bands all have to do the same motion, right? They have to be in step. When you go over a bridge, what happens is if you match the natural frequency of the bridge that you're going over, it's going to cause that bridge to oscillate more. And that can collapse the bridge. So generally, what people should tell you when you're going over a bridge in a marching formation is to break your steps. Because you do not want to match the resonant frequency of the bridge. It may cause the bridge to oscillate so much that it will fall. And that's what happened to the Tacoma Veras Bridge in California, where the winds were so high that the bridge actually fell. Another very important term is called delta F. It's also called the full width half maximum. I'll talk about that later. But for right now, you have to remember that it's called the line width or the bandwidth. And you want your system to be driven slightly above the bandwidth to maintain maximum amplitude. It's actually 71% of your maximum. So for a lightly damped system, your amplitude will be very high. So I want you to write this down and that down. So this gives you a very good relationship. So if you look back, delta F was A max divided by square root of 2. For a lightly damped system, you will get a very sharp peak. Your amplitude will be large and your line width will be small. Whereas for a heavily damped system, you will get a small amplitude, but a very large line width. So for most electronic equipment, you have to find the balance between the two. Another term that is very important for physicists and engineers is what is called a Q factor. A Q factor, given by this equation, describes the energy damping for any oscillating system. It compares how long it takes for something to decay to the amplitude of the system. If you want your system to vibrate longer, you want your Q value to be as large as possible. And so this picture helps me remember. So you want your Q value to be as large as possible if you want your oscillations to die out slowly over time. And Q factor is given by F0 over delta F. So that's a picture you should keep in your head. The higher the Q value, the slower the damping decay. So think about it. Better quality means larger Q. Worse quality means lower Q. So this is like if you were playing your guitar. So if with Q equals 0.2, if you were playing your guitar, what would that sound like? You want a sustained sound, right? Out of your guitars and out of your piano. Like if you press your piano key, do you want a long, nice melodic voice, or do you want just, that'll be very disturbing. Right? It just disappears immediately. So you want your Q value to be as large as possible. Now let's do this question. So a particular oscillator has a resonant frequency of 400 Hertz and a Q factor of 20. What's the bandwidth of its resonance curves? What's the formula that we have? This way, F0 over delta F. What was delta F? Line width. What is F0? Frequency or fundamental frequency or resonant frequency, all the same words. And this is the Q value that we're looking for, right? Okay, so now what does it say? It has the resonant frequency of 400 Hertz and a Q factor of 20. What's its bandwidth? Q factor equals F0 over delta F. It gives me 20 for my Q factor. It gives me 400 for my resonant frequency, and I'm looking for delta F. Thank you. Hertz. So its full width half max is at 20 Hertz. So you want your system to be above that.